Okay, I think we might get started. Welcome everybody to the JKMRC Friday Seminar Series for Friday the 8th of May. My name is Nathan Fox from the D.H. Bryan Mining and Geology Research Centre at the University of Queensland. In person today at the JKMRC we have Professor Rick Valenta. He's the Director of the D.H. Bryan Mining and Geology Research Centre, and he's currently the Acting Director of the JKMRC as well. Thank you everybody online for joining us. Before we begin, on behalf of the SMI and the University of Queensland, we're based here in Brisbane, and we'd like to acknowledge the traditional owners of the lands on which we meet today, and we pay our respects to their ancestors and their descendants. Today, it's a pleasure to introduce our guest speaker, Daniel Hastings. Daniel is the Director and Principal Consultant at Quantified Strategies. Daniel is a mining professional. He has extensive experience in exploration, technical services, mine planning and geology in both site-based and corporate roles. Daniel's worked on projects across Australia, Canada, the Philippines and Africa. And that also includes more than 6 years working as leading the geology and managing exploration at Octedi in PNG. Daniel's roles have spanned management, production and planning, working on a range of commodities, including base metals, battery materials and gold. So Daniel holds a Bachelor's of Science in Applied Geology from UNSW, a Bachelor of Law with an environmental major from Macquarie University, and he holds graduate certificates in mine planning and applied finance. Daniel is also currently undertaking a PhD at the Sustainable Minerals Institute in the area of system dynamic modelling, assessing the impacts of social and economic aspects on mining. Daniel is a member of the AusIMM, the Australian Institute of Geoscientists, and he is a competent person for JORC 2012 in mineral resources and ore reserves. So bringing all of that experience to the table, in today's seminar, Daniel will be discussing the importance of cash flow modelling in strategic mine planning. Before I hand over to you, Daniel, I just wanted to let everybody online know if you could please ask questions in the question and answer section of the Zoom panel, and then we can moderate those to Daniel towards the end. Okay, thank you, and over to you, Daniel.
Thanks, Nathan. Okay, so today I'll just give a bit of an overview on cash flow grade modelling. I'm not going to get into much detail, but just see how we go. Second will work. Does not want to change slides. There we go. So, what is cut-off grade? Generally, it's what we use to decide what's ore and what's waste. People use this term quite a lot, but quite often they get confused between cut-off grade and break-even grade, or sometimes even at what they call a cut-over grade. Originally, back in the 1950s, a guy called Mortimer, a South African guy, was probably the first guy that tried to define cut-off grade. He had two definitions, one being the average grade of the ore must provide a certain minimum profit per tonne, and that the lowest grade of the ore must pay for itself. We've come a long way from there, but the problem you run into with these things is that quite often in an operational sense, people start to say, well, you know, waste plus ore equals more ore, and that can get you in a lot of trouble. I've seen that at a lot of operations. Especially when cut-off grade is confused with break-even grade. A lot of companies go under when that happens because your average grade that you're being fed to the mill starts to approach your break-even grade, and then profit starts to fall. So that's why a lot of times people will say, you know, the junior mining engineer is the one who decides the CEO's bonus. It is important to note that cut-off grade is actually an outcome of a planning process. It's not an input, because what you want to do is you want to optimize your profit. And you have to go through a whole process to do that. And then the outcome of that process will be a cut-off grade policy. The other thing that's important to note is that cut-off grade is not cognizant of a couple of things, and that can be quite important. It's not cognizant of time, and it's not cognizant of strip. They're the two main ones. It also doesn't provide information on things such as the optimal process route in terms of a multi-route system. So yeah, that's, oh, we've moved on, Britt.
Yeah, I think you must have hit the keyboard there,
I think it's a delay thing. So the importance of cut-off grade policy. Well, cut-off grade policy determines your profit. You can use it to assess value at risk. And if you get it right, the policy right, you can decrease that uncertainty, and it's used to increase return. So with capital allocation, you'll see that chart there with the blue boxes. It's a very common chart. You see it mostly in estimation, grade estimation models. And if that ellipsoid represents all the blocks in the model, what you're trying to do is squeeze it so that you don't get misallocation. That's true for grade estimation, but it's also true for cutoff grade or block value estimation. So the more accurate your modelling, the more you'll reduce the material that sits inside those blue boxes. And then that'll help you improve your strategic planning and decrease risk. If there is a bias in the data, you might find that you're leaning towards one way or the other, perhaps more towards putting waste in the mill or more towards ore to the dump. There's information around that can help you decide or help you understand if that's the case. Those two smaller charts there are just grade tonnage curves. They're two real grade tonnage curves from gold operations. And what they're showing, I guess, is that the top one shows that at the break-even grade or at your cut-off grade, small movements result in large tonnage movements. So if your cash flow grade modelling is off, it has the potential to move large amounts of material from either ore to waste or vice versa. The other curve shows that down in those lower grade areas, there's very small, relatively small movements in tonnage. That's probably more representative of something like a narrow vein gold project where material that's ore is definitely ore, and there's a clear distinction between mineralisation and unmineralised host rock. If this works now. So looking at cut-off grades over time, originally people just used to use a simple cut-off grade that pick a point, 0.5% copper or 1 gram per tonne gold. Then it was people moved towards an in situ value. That's especially useful where you had multiple commodities in the deposit. So you get a metal equivalent value. The problem with that is that it's in situ, so there's no account of processing, recoveries, costs. Then people started to use a net smelter return. So that's essentially the revenue that you gain from the smelters or from the sale of the product. That includes marketing and logistics costs, but again, it doesn't include a lot of the operational costs. Then people started using net smelter return per mill hour. What that does is that allows you to move your cut-off grade policy to your constraint. So you understand within your whole system where your constraint is, and you try and maximise utilisation of that constraint. Then there was net value where they add in costs, improve net value, so you start getting into a lot more detail, and then ultimately to a cash flow grade, which is a full value assessment. I've just put a number of papers there that talk to all of these things. There's really not a lot of literature out there on cut-off grade and cash flow grade modelling, but they're the main ones that are out there. You'll see there's Brett King and Ken Lane, Jeff Whittle, the names that you usually associate with this stuff. So that's just a little bit on cut-off grade. And so just to show you why it's important. So this is an example. I pulled a couple of blocks out of a real model of a large operation, a porphyry copper operation. You can see here these two blocks, depending on what you use as your cutoff grade, it depends on which block wins. If you just use a straight copper cutoff, block 1 would win. If you use the straight gold cutoff, block 2 would win. If you use the copper equivalent or the in situ grade, then block 2 would win. If you went to a net smelter value, then block 1 would win. So you can see that as you go down the list and you calculate all these different metrics, the block ranking, which block is better than the other, will move around. So this can be quite important because it'll have an impact on pit optimization, pit sequencing, schedule optimization, stockpiling. I mean, in this particular instance, both these blocks are ore. There's really no doubt that both those blocks are ore, but the ranking of them is quite important. There are a lot of things that change this relationship, a lot of inputs that will move these blocks around. And that's why we often talk about having a variable cutoff grade, not a fixed cutoff grade. You can't just pick a straight 2% copper that's a fixed cutoff grade. You want a variable cutoff grade that moves with the different attributes that are used to generate the metric that you use for your cutoff grade. This is another block. This is where it gets a little bit more important. So these are another pair of blocks that I pulled out of the same model, but these blocks are on the margin. So again, if you were to look at block 1, it's got a higher copper equivalent grade at 0.56, and it's got quite a large net smelter return per mill hour. But when you calculate its cash flow grade, it's negative, meaning it's waste. Whereas block 2, which has a higher copper grade, but lower copper equivalent grade and lower net smelter return per mill hour, it actually does get designated as ore. So that's where you have these, especially in a large open pit deposit like a porphyry, where your grade tonnage curve flattens out. Around the margin there, you can move massive amounts of tons by changing some very small variables in your cash flow grade model. And this will impact the operation and the profitability quite a lot. So what drives these variances? Well, this is a bit of a list that I just pulled together. Some of the inputs that we use in deriving a cash flow grade model. The first question that you have to ask yourself though is which of the inputs need to be accurate and precise and which just need to be fit for purpose, and how much contribution do they give to the overall model. I think most of these variables in the center box, the throughputs, the recoveries, the costs, they're fairly well understood, especially by metallurgists and other various people in the mining industry. Costs are pretty well understood. The one that might be a bit more problematic are the regulatory constraints, especially in terms of how you get them into a cash flow grade model. But things such as AMD, where a parcel of material has a potential to create acid, you can model that and you can attribute a value to it. In some cases, it may be preferential to process material that's slightly below the cash flow grade cutoff because it's more cost effective to do that than to treat it as waste because of the rehab costs, and you wouldn't know that if you didn't model it. So a lot of these inputs, although fairly well understood, it can get quite complex, and that's why you really need to understand this idea of fit for purpose, what's important and what's not. The other thing that I thought when I put this list together is that all those variables look pretty familiar. And I thought that's where I've seen them before. It's all the modifying factors in the JORC guidelines, which makes a lot of sense, right? I mean, that's how you go from a mineral resource to an ore reserve. You apply the modifying factors and you determine what's ore and what's waste. So in terms of cash flow grade modelling itself, right? So what we want to do when we produce a cash flow grade model is we want to model all possible outcomes for a block so that we can then make decisions on where that block goes. And I suppose I should just mention here, this has quite a large impact on operations. I've done this on a number of different operations around the world, predominantly large open pit operations. But cash flow grade modelling as a component of the overall planning process, I've seen real swings in NPV or in value of over $1 billion. And this type of work's led to investment by companies, real investment of hundreds of millions of dollars in various expansions or changes to processing. And it all starts with the cash flow grade model and understanding where the value lies. So all these possible outcomes, from all these possible outcomes, a cut-off grade policy can then be identified that meets the business requirements. It's not always maximising NPV, but it probably should be. You do get the odd occasion when NPV is not the objective function, but I'd argue quite strenuously that maximising NPV should always be the objective function. Companies that don't have maximising NPV as their objective function quite often do run into trouble. You know, there was a time there where I know some of the gold majors focused on actual production. They wanted to hit certain levels of gold production, and that became their primary driver, and they ran into some trouble. You know, there's other producers that focus on mine life. There's other producers that focus on volume. You know, they want to own the market, flood the market. And it doesn't generally work out well. Like I said before, it's important to recognise that a cash flow grade model is not cognizant of time, and it's not aware of the cost of exposing a block. They come later in the form of pit optimisations and schedule optimisations. Mine modelling can be problematic, but it's generally straightforward. And those initial comments there, these I think are some things that you sort of have to live by when you're doing this type of modelling. The first is, as George Block said there, all models are wrong, but some are useful. It's certainly true of all models, I would suggest. Start with the end in mind and collaborate with the client. In this case, the client is usually the pit optimisation and the schedule optimisation. So understanding what's required from the cash flow grade modelling as inputs to downstream processes is very important. So that's why you need to collaborate with those areas. Quite often you'll see in some companies the geological models owned by the geologist and the pit optimisation and schedule optimisation models owned by the engineers, and they don't really talk. They just say, here's the model and hand it over. That really doesn't work too well. You've got to undertake continual testing when you're building these things. I'm sure all the Mets will be very aware that it's best just to follow the material flows. If you try and do things the wrong way around, it never really works out. And I would suggest to be as verbose as possible with coding. So keep a lot of documentation, a lot of notes, because you won't be the only person that works on this kind of stuff, and terrible when you get these massive models. Cash flow grade model can run into thousands of lines of code and you just handed it. They're quite hard to decipher. I suppose one other thing is when George Box first said all models are wrong, but some are useful. The first thing he said is since all models are wrong, scientists cannot obtain a correct one by excessive elaboration. I think that goes to this idea of being fit for purpose. Yes, it can get quite complex and you have to model it, but try and simplify it as much as possible. But a later paper, the second paper he wrote there in '79, I think he had a much better quote in there saying, since all models are wrong, the scientist must be alert to what is importantly wrong. It is inappropriate to be concerned about mice when there are tigers abroad. In all of these things, you've got to be aware of what's moving the needle and focus in on those things that actually do contribute a lot of variance. All the other stuff, just make it fit for purpose. Okay, scope. So when you start producing a cash flow grade model, it's very important to understand scope. Rarely you'll be required to do a model that only covers an operational department, such as the mill or the mine, or environment. It could be any of those. Most often you'll do it on a deposit type scale. You may do it on an asset scale where you've got multiple processing facilities across multiple deposits, but they're all in the same area. So think things like coal or iron ore. Sometimes it'll be done across a whole business unit where you've got, a copper business unit that has multiple copper mines in multiple locations. And sometimes you can undertake cash flow grade modelling across a full value chain. Areas where majors have built downstream processes like smelters. It's interesting how the value of the material changes when you start adding in all these different processes. If you're producing a concentrate and you stop at the concentrate level where you're just selling a concentrate, as opposed to actually owning a smelter and optimizing for the downstream as well, you can get quite a lot of movement of material and in block ranking. So you really do need to be clear about what section of the process you're going to model. Also understand the temporal resolution of your model. So a strategic mine plan looks at the life of asset timeframes, and you need to use long-term averages. Short-term applications, so a cash flow grade model can be applied to short-term applications. It's quite good to get alignment across all the different timeframes, from grade control all the way through to strategic planning. But the short-term applications generally require more detailed inputs and can vary a lot more. If you change your input parameters all the time, because I have been in operations where every month they'll update recovery models based on the reconciliations, it just becomes unwieldy, especially when you're looking at the longer term strategic plans. You just want to look at averages and look at the big changes. And if you do change all the time, then there's a cost to that. Every time you change your cut-off grade policy, it's going to cost you in terms of how the operation's set up. I think people here understand the benefit of stability. I know a lot of metallurgists are always talking about keeping the mill stable. It's the same in the planning context. If you keep things stable, then it's much better outcome for the business. So underlying the cash flow grade model is the mineral resource model. Geological block models are usually built on a single lithology domain but can use other domains. I have seen on a number of occasions where the input information to the cash flow grade model is actually done on blends. They're not done on the domains used in the geological model. And that really, really hurts. You need to understand what the underlying data is, and provide inputs that can be built on top of that. I know metallurgical domains is really where you want to end up, but generally there's not enough data to construct those. So you need to be talking to the geos a lot. And again, you need to look at longer term averages rather than short term variances. So once you've got the block model, you need to then model the process route. So this is just a flotation circuit. Trying to model that in terms of material that's passing through it. You can make it as easy or as difficult as you want. Once again, it needs to be fit for purpose. What's driving the value? Is it throughput? Is throughput driving the value, or is copper recovery driving the value, or is gold recovery in flotation, gold recovery in a gravity circuit? And again, this is where everybody needs to be talking. The Mets need to be talking to the geos, need to be talking even to the enviros and the bean counters. The other thing is, how do you simplify this up? How do you group it into digestible chunks? Obviously, you wouldn't want to model the roughers and the scavengers and the cleaners. You just have a recovery curve across the whole flotation circuit. I don't think there'd be any point in going any more detailed than that. But then things can start to get a little bit more complex. This is just a CIL circuit. Here you might model the crusher area, then you might model comminution, then you might model the leach circuit. I don't think you'd model the electrowinning or smelting or the inline reactor separately. It would all be in one. And then you start to get really complex. So here we've got CIL, we've got flotation, we've got an autoclave. How do you model that? And like I said at the start, you have to model the material going through every process route. So there might be multiple paths that the material can take, and you need to model each one of those paths so that you can understand what is the best path for it to take, and if you need to do trade-offs, then what that trade-off is going to cost you. So again, the metallurgical model needs to be fit for purpose with recovery curves. I would also mention there that don't just focus on the payables, focus on the penalty elements as well. So many times they build these things and there's plenty of recovery curves for all the payables, but nothing for the penalties. There's also the distinction there between the metal recovery curves and mass pools. I've done cash flow grade modelling on systems where you concentrate up product, and also where you concentrate up gang and take the tails as your product. Figuring out where your fixed inputs are. A lot of different projects will have constant tails or constant concentrate grades. When you see those, you need to be able to flex them and do sensitivities, and again, find where the value is. Throughputs are quite interesting. Throughputs should only really be the primary bottleneck, but quite often in an operation they'll say, oh yes, our primary bottleneck is the SAG mills. And then when you look at it, it actually might turn out to be the ball mills, or it might turn out to be crushing, or it might turn out to be the product pipeline. And if you don't have throughputs for all those different points, then you can't do a full assessment. And then you won't be able to, show or be able to provide justification to people as to why they should spend capital on deconstraining certain areas of their process. It's always good to have your costs down, especially fixed and variable. If you don't have fixed and variable costs, then you can't enable differentiation of the throughput impact. Obviously, material that goes through a process plant a lot quicker than other material is going to have a lower unit fixed cost, and that's important in terms of determining its cash flow grade. The other thing is that the metallurgical modelling that's used in the cash flow grade model needs to align with operations. A number of times the model that's provided is not actually the model that the operations guys use, and that runs into some serious trouble as well. And like all things, and like I've been saying before, if you keep on talking to people, then you usually solve all of these discrepancies. Just to give you a very quick example, this is how we do it. We do it in Python coding. This is just a little bit of code setting up the recovery inputs for copper and gold and fluorine. You can see there's the comments up the top, trying to keep the naming easy to read. And then this is just setting those recoveries for every block. Again, there's all the green comments down the side saying what's going on, so you can read it quite easily. This is looking at throughputs for 2 different iron products. There's a direct reduction pellet feed and a blast furnace pellet feed. Different lithologies have different throughput curves, also for different products. So all of that needs to be modelled. Like I said before, these scripts that we generate can run into thousands and thousands of lines of code. So they do get quite complex. I've said this before, you need to calculate every possible outcome. Then what you should do, and we call it the US Marines, be the best you can be, where after you've generated every possible outcome, you'd report it out as the best possible outcome for each block, and that will give you the block ranking. And then that block ranking should be done, it should be used for the pit optimizations. The simple reason why you do that is that you have to plan for success. If you're not planning for success, then I don't know what you're doing, but it's probably not the right thing. Inevitably, you won't process that material. If there are multiple pathways for material to be processed, inevitably you won't process that material in the best possible route for that individual piece of material, because there's a lot of other components to the value for the business, opportunity cost, the value of time, strip. The other thing that's really good is to pre-calculate all of this so that when you hand it over to the pit optimization, schedule optimization, they don't need to recalculate it. The schedule optimizations at the moment can take a very long time. Even with the computing power that we've got at the moment, I've seen schedule optimization programs that take weeks to run. And if they have to recalculate all of these outcomes, these value outcomes for the material, it can really slow them down. Whereas if you've got a cash flow grade model that's holding all of those possible outcomes in there, then the schedule optimization just gets to be able to pick and choose which outcome provides the optimal solution in terms of maximizing NPV. Units are very important. Units are very important because block models, which is the basis for the cash flow grade model, are often coded for mining shapes. So after you've done your pit optimizations, you'll have a pit, you'll have cutbacks, you'll have stages. And these have to be reported out as inputs to the schedule optimization. When you when you export these things, these shapes, the material contained inside these shapes, it all has to be weighted correctly. If you store in the model everything on a per tonne basis, then it becomes very easy. Quite often though, we store things on a per hour basis or a total value basis, or a dollar per tonne or a dollar per hour, or a total mass. You need to be very careful with the units when you're moving around. I've seen that cause quite a lot of trouble as well. There's also cases where, especially when you're dealing with really complex downstream processes, where you can't carry values in a model. You need to carry multiple values to then calculate, further downstream what that value is. So again, you need to be very cognizant, very aware of this, and understand those values, those units really well, because it'll tie you up. So things like arsenic grade of a concentrate seems fairly straightforward, but if your concentrates volumes are changing with your block and your recoveries are moving in terms of your underlying payable versus your penalty, because you're trying to increase your payable and decrease your penalty, and then you've got to slap them together and get a grade that's based on a product, it can be quite difficult. So just be careful of that and make sure that all the units are correct. Some other stuff. All right, regularization. Regularization of the model. So a lot of models are built as partial models or sub-block models. For the process of strategic planning, the models really should be regularized. So regularization essentially takes into account all loss and dilution. A pit optimization, not that I've seen, works on a sub-block model. There's also correlated versus disconnected price movements. Pricing is going to change all the time. And like I previously said, in terms of temporal resolution, you don't want to be changing the model all the time. But if price movements are correlated, if you're in a multi-element, multi-commodity environment, then a price movement won't make any difference to your cash flow grade policy, because your block ranking won't change. Block A that's better than block B will always be better if the price movement is consistent. The problem that it happens is sometimes commodities will diverge. So in a copper gold system, for example, copper and gold track relatively nicely together, and then they might diverge. Copper goes up, gold goes down, and vice versa. And that will change your block ranking, and that will require rerunning the whole process. So watch out for that. Marketing. Marketing can be an issue. I've had issues with marketing before, especially where there's this transfer pricing, where companies are trying to maximize profits through marketing instruments. Just be careful with that. And then product specifications. So not everything is just a concentrate or bullion, or sometimes there are other product specifications. So the one that I've worked on most is the graphite concentrates, where size distribution is a major component. And then also in garnet sands or silica sands, where the actual particle shape can be important. But that's just a metric. You have measurements, you have a model. You've just got to make sure that it flows through. So, for example, here's a graphite concentrate. So this is using a fairly standard distribution model that estimates the various size fraction of the concentrate. And this model actually had a very good correlation. I had an R-squared of about 0.97, which is pretty good. And then So this is about it. Traps for new players. Topography. You've got to watch out for topography. This can be a real issue. Mostly because of discounting. If you get your topography wrong, and this goes back to the idea of mining shapes and block partials and getting your tonnages right, if you get your topography wrong, it will bite you, because that's where you start mining, and that's where the discount rate is most attractive, and you're going to make the most money in year one. And if you don't get the topography right, you'll either overstate it or understate it in terms of value, and it will have a big effect. Again, units, you've got to make sure those units are all okay. Beneficiation and ore sorting is being used a lot more, and those type of processes can also be quite problematic in cash flow grade modelling. The only advice I give you there is follow the metal. Although that's good advice for the entire cash flow grade modelling process anyway. Mass balances are always really good. Blending is another one. Blending can be really complex as well. Usually it is a capacity problem. The autoclaves is a classic one. It's also a classic one in terms of value. A single block of gold, let's say, it's easy to calculate the value of that, but when you require a certain amount of sulfur to activate an autoclave to get it to run, you'll see that there's waste blocks that actually have a value and enable you to access ore blocks that otherwise you would not be able to access. That's a blending problem, and that can be very complicated. So you just got to sit down and think about it. Again, mass balances are good, and go with the material flow. Start at the beginning and work your way through the process. The last thing I'll say there is factoring. I've seen it time and time again where you get given a model, you put the model in, and the operations guys go, this isn't reconciling because their model has management factoring on it, or some type of factor that they say, oh yeah, no, the model says that this is going to be the gold recovery, but we don't believe it. We always get an extra couple of percent here, or we lose a couple of percent there, so we just factor it. Whatever you do, just don't do that. If there is a bias in there and it's a consistent bias, then they should be able to adjust the model appropriately, not just add a factor but redo the curves. And that's all I got.
Thank you. Thanks, Daniel. Okay, so I'd just encourage anybody online, if you have questions, please ask them now. Daniel, we've got questions already coming in. The first one from Tim Napier-Munn, just asking just commenting mainly that the metallurgical models that you have used seem quite detailed. In your experience, where are they deficient, and how would you like to see them improved?
Quite often, I've seen them deficient in terms of what generally happens. The best sample that the Mets have when it's an operation is the mill. So they'll take belt cuts and other samples throughout the processing plant, and from that they'll derive their curves or their throughputs. The problem is that's almost always blended material. So they'll say this is 20% skarn and 80% porphyry, and I say, well, that's fantastic, but the underlying geological model only has either porphyry or skarn. It's not a blend model. I can't really do anything with that. It sounds quite straightforward, but that really happens quite a lot. The other thing is throughputs. A lot of the time, throughputs are just a fixed value. They'll say for this rock type it's X, and for this rock type it's Y. I'd really like it when people have done a lot more work on throughputs and they can give you a curve, because that really speaks to value. It's kind of like in a geological model, people spend a lot of time on the elemental data, the assay data, and not a lot of time on the SG. But they both have the same impact to the model in terms of metal. So METs will spend a lot of time doing recovery curves and not a lot of time doing throughput curves, but they have the same impact, generally the same impact on the operation. So that's probably the two main ones.
Yeah. I think that kind of, there's a comment here from Ralph Smith, just also, I suppose, feeding into that, just saying, should we also not model throughput rates, such as material, things that might affect throughput rates, such as material hardness, etc., and associated costs? So I think that you've probably included that as well in your.
Yeah, absolutely.
Yeah, be good to be able to do that. The question from Paul Gow, he's just wondering, he thinks you mentioned that in some cases the cash flow cutoff is based on blends with reference to domaining of this mineral resource model. Could you explain or elaborate on that?
In terms of blends, I'm not quite sure. I mean, the underlying data, like I've said before, that come from the Met sometimes is blended data. Each block in the block model is only a single lithology. When it goes into the schedule optimization, obviously it's blended up. What can happen though in terms of blending is like I was saying about the autoclave, or another one that's really interesting is at Octeti. They have a pyrite flotation plant that pulls the pyrite out of the tails after it's been through the copper concentrator for environmental purposes. Yeah, that's one of these regulatory things that you have to be cognizant of. But if I've got two blocks, for example, one block's got very low sulfur and one block's got very high sulfur. If I push them through the process, the high sulfur block will max out on the recovery, and the tail coming out won't meet specification. It'll be too high a sulfur in tail. But because it's a capacity equation, the block that had very low sulfur in it, you can use some of that capacity to take the sulfur out of the other block. So it's a blending issue. Together, the two blocks are fine. If you treat them separately, it doesn't work when you model it. That's the blending problem. So how do you get around that? What you actually need to do is you need to set multiple outcomes for every block. So you say, this is what happens if the block goes through by itself, and just use the primary underlying curves. And then you say, but if I send that block through and there's a lot more capacity there, then I theoretically recover all of the sulfur that I need to, then this is the outcome. And then post cash flow grade modeling in the schedule optimization, you can aggregate up all of these things to a total volume and use that as a constraint on the process. So again, it gets very, very complex, and it takes a long time to get your head around it. But yeah, that kind of thing can be done. The other one, of course, is the autoclaves, where you've got in a gold system like Lahire, for instance, you've got the gold in the autoclave, you've got the oxygen, and you've got the sulfur, and you need to get them all right to have the thing work properly. That's a bit hard to model in a block model that's just got a single lithology in each block and a single value attributable in terms of revenue. How do you say that a block that's got sulfur in it that's required in the autoclave to make it work properly, but it's not actually contributing any metal? How do you give that value enough that it's actually determined to be ore and not waste?
So in a kind of related subject, Douglas Mazzini is just wondering, in the conventional block model, if they consider dollars per block typically, should we consider, in your opinion, dollars per tonne of concentrate produced per block, or dollars per hour needed to process the block? Should we be attributing these blocks in different ways in the future?
Oh, I certainly would. If all of your material, like I say, different deposits have different requirements. If you're certain that all of your ore material is always ore and always going to be ore, because it contains so much value, and there's a clear distinction between ore and waste because of the mode of mineralization, perhaps, then you don't really need that complexity. But if you have areas of low grade and your grade change curve is such that moving the cutoff does pull material in and out quite a lot, then I would very highly recommend that you go to a complete cash flow grade model. You can do it in stages. You can go from $1 per tonne. If you go then to a net smelter return per mill hour or per hour of your bottleneck, then you'll start to see, where you can optimize the system and where you can add more value by really utilizing that bottleneck properly. And if that bottleneck's stable, then fine. If it's moving around, you need more and more data to see where that bottleneck actually truly lies and what you can do to deconstrain the system.
Excellent. Michael Horton was just wondering if you could expand on the effects of topography and how it can become a big problem. I'm sure you've got a lot of experience in this firsthand.
Okay. So if you, for instance, are working on a model and you take the view that you're just going to do block in, block out, so either you take a block or you don't, but the topography actually cuts a block in half. If it cuts a block at 51%, let's say, 51% being in situ and 49% is actual air. If you do block in, block out, then you're going to take the entire block. Now, a lot of people say, oh yeah, but it sort of shakes out in the wash, it's slippery dips and roundabouts. It doesn't work out that way because you're actually attributing all this value to the 49% that's really air, but you're taking that value. And because your schedule starts at the top, at the topography, you're adding in those additional tonnes in year one, so they're not discounted. So you get really wrong answers in years 1 and 2. So you really need to adjust for topography properly and make sure that you're carrying the right amount of material. Otherwise, you will run into trouble. You'll have a year 1 that has very low material movement but meets all of the requirements in terms of metal production, or vice versa. You'll have massive material movement in year 1 and you won't be able to hit your targets. So that's all going to be a topographical effect.
Okay, thank you. And a question from Joe Kakaza, just commenting that metallurgical models are difficult or limited by lack of data. Then how do operations actually develop the models across, I assume across an asset, or how do they actually develop these models when they are lacking data?
Lack of data is not necessarily a problem for developing a model. You build the model based on the flow sheet, based on the material flow. If you don't have data, for a certain input, then you go and ask them and say, well, what's your best guess, or what data do you have? And then you do a sensitivity around it. And you might find that really they don't need that data because it doesn't move the needle very much. Or if it does move the needle a lot, then you go back to them and you say, look guys, this is a serious issue. Can you please go and spend some money and try and narrow down this input, because you are having a massive effect on the project or the operation. But you always start with what you've got and you do the best you can. And even that, I would suggest moving from a simple cut-off grade $ per tonne or in situ value to a cash flow grade model will add value.
Excellent. Quite an important point here from you and Sellers, Mining 3. I suppose it's going to become much more relevant moving forward. He says that you've stated that it's best to keep the cut-off grade constant, but then how do you cater for selective mining approaches? An example of grade engineering, well, I suppose that cut-off grade is constantly changing depending on what you do with that material.
Yeah, well, I suppose I didn't explain it really clearly. A fixed cut-off grade historically was simply, a grade field. So you've got 0.5% copper or 3 grams per tonne or whatever it may be. When you go to a variable cut-off grade policy, if you use cash flow as your cut-off, so anything that's positive in cash flow is ore and anything that's negative in waste, it's fixed in that 0 point is the point at which you differentiate between ore and waste. But it's not fixed across the deposit. Every block is calculating its own cash flow grade, and you can't it is a variable model, because like I showed in those slides where I had the two blocks, one has a higher copper equivalent than the other, yet one was ore and one was waste, and it didn't necessarily make sense. So that's the kind of variability I mean. In terms of the fixed cut-off grade, is if you calculate it all out, the fixed portion of it is if you make money, you're ore, and if you don't make money, you're waste. That sort of helps.
With that in mind, I mean, how do you think approaches to modelling deposits, even from an exploration perspective, and then resource development, when you try and build a JORC compliant resource, do you find that there may be some deposits that don't, on paper, look as economic as others, but when you actually start mining them, the opportunities costs come in, and the technologies you apply can actually transform these into economical mines?
Yeah. Again, it's got to be fit for purpose. So you start with what you've got, you build them as simply as you can, and then as you get more information, you add more in. You can't make them complex just for the sake of it. But what I have seen is that when you actually do get all of the detailed data, like I said before, I've seen the needle move on projects over $1 billion, and then gone on to show that that's a real movement. This is not something in a development case that we're looking at. These are real operations that are operating, and then that's led to major investment and real changes in terms of their cash flows and their profitability. And I've seen it go both ways. I've seen it add a lot of value, and I've seen it destroy a lot of value, or at least destroy what they thought was value. So yeah, if you don't have the information, you just do the best as you can. But as you get more and more information, you need to keep on updating this process and get better and better at your model. If you don't have enough information to do a cash flow grade model, then just do a net smelter return, or just do an in situ value. And that's the information you've got, and you've got to make the best decision you can based on that information.
Okay, I think with that, thanks again, Daniel. Really appreciate your time this morning and the interesting talk.